Good evening, everyone, and welcome to the March 2025 Journal Club. Tonight, we're quite honored to have a guest speaker, Katie Williams from Crow Canyon Archaeological Center. And she's working in geospatial archaeology and is going to be giving us a presentation tonight on LiDAR and archaeological visualizations in the central Mesa Verde region. Take it away, Katie.
All right. Thank you, Greg. So I wanted to start by saying thank you for inviting me here and for giving me a chance to share a little bit of what I know and what I've been learning about LiDAR. As Greg mentioned, my name is Katie Williams. I am graduating this semester from the University of New Mexico. My dissertation research focuses on understanding how people worked together to build their houses and other spaces at the communities of Batatacan and Quetzal in northeastern Arizona. And I have a special interest and focus on earth and architectural materials, and more specifically, mortars, plasters, and daubs, and kind of understanding those on a recipe level and from a micromorphological perspective. But I am presently working as the postdoctoral scholar in geospatial archaeology at Crow Canyon Archaeological Center up here in Cortez, Colorado. I've been working with Grant Coffey, whom I'm sure many of you know, and I've been learning a lot about LiDAR and about how archaeologists use LiDAR and how we visualize the landscape using LiDAR. So let's see here. See if my slides go. Okay. Before I jump into my presentation, I did want to start by sharing Crow Canyon's land acknowledgement with you. So our land acknowledgement says, the Crow Canyon Archaeological Center acknowledges the Pueblo, Ute, Paiute, Dene, and Jicarilla Apache people on whose traditional homelands this institution sits and upon which we work and reside. Our mission-related work would not be possible without Indigenous people in the past, present, and future. We respectfully recognize and honor ancestral and descendant Indigenous communities for their contributions to all humankind. We bring light into the darkness of memory that these lands, waters, wildlife, and her descendants hold as a result of policies of removal, genocide, and displacement. We hold the disciplines of anthropology and archaeology and our organization accountable by taking a critical approach to our work that allows for difficult discourse and shifts our efforts to be inclusive, restorative, and just. And to that, I just wanted to add that in the context of my work as a geospatial archaeologist here at Crow Canyon, a lot of what this looks like in terms of shifting towards a more inclusive, restorative, and just archaeology involves being very critical and conscious about the data sets that we have access to and the research questions we're trying to answer, as well as the impacts that those research endeavors have on descendant communities. And more specifically, in the context of the LiDAR point clouds I'm going to be talking about tonight, these are kind of what we're starting to refer to more and more as big data sets. And it's really important in the context of these big data sets that we have conversations with descendant communities around data sovereignty and data governance. So Crow Canyon is starting to have some of these conversations through a working group that we've put together to tackle some of these larger issues and how our work can articulate with a more inclusive, restorative, and just archaeology. So just to give a quick outline for what I'm hoping to talk about tonight, and I did practice and I came in right at time, so we'll see how it goes here in the live run. I'm going to start by talking a little bit about what LiDAR is and why archaeologists use it, and this may be old news to some of you. But I'm going to also talk a little bit about the technical aspects of LiDAR and everything from how we gather or acquire point clouds up through how we actually process those point clouds and come up with our derivative raster products that we use for our visualizations. Then I'm going to go into a little bit of detail about the project I'm working on currently here at Crow Canyon and some of the things that we're seeing on the landscape through this LiDAR data. And I'm going to end by talking specifically about visualization for archaeological topography and hopefully giving a better example of how that works and why we might want to use it. So to begin with, LiDAR stands for light detection and ranging, and I'll get into the technical aspects of that process momentarily, but I wanted to talk a little bit about how LiDAR is used by archaeologists and why we use LiDAR And I have here kind of a visual example to accompany this, but generally, we use LiDAR in either a visual sense or in kind of a quantitative or semi-quantitative sense. And most of this presentation is going to talk about or focus on the visual sense of LiDAR and LiDAR use. But it's important to emphasize that LiDAR is really just a collection of elevation data. And so when we're using LiDAR, we're really using elevation data. And archaeologists can use this elevation data to understand anything from how water moves across a landscape through hydrological modeling, which can help us with understanding subsistence practices and where people might have placed agricultural plots, for example, or even why in a certain area we're not seeing archaeology. Perhaps there is a drainage that has led to erosion and loss of architecture. We can also use this elevation data to think about how people would have moved across the landscape. And this is generally done through least cost paths modeling. People will look at different routes that might have been more or less energetically costly, or costly in terms of time, for getting from point A to point B. But we can also look at elevation profiles, and this is something that has been done fairly often in connection with work on the Chaco roads, and deriving profiles that can be used to help identify when we're seeing features on the landscape, whether they really are what we think they are, meaning roads, or whether they might be something else. So that's kind of on the more quantitative to semi-quantitative side. And a lot of those aspects of the work I'm still learning about. So I'm going to kind of steer clear of them, but I'm also happy to answer questions if any come up at the end. In terms of the visual analysis of LiDAR, LiDAR can be used and is increasingly used for a whole range of tasks, from the documentation of architecture and actually mapping out individual masonry units, for example, in a wall, to large scale, like landscape scale analyses covering entire counties or entire states, or even the entire globe, depending on the resolution that you're working at and the questions that you're trying to answer. Most of the time when, in this particular presentation, I am going to focus more on the landscape perspective. When archaeologists are using LiDAR for this visualization work, we tend to use what are called bare earth digital elevation models. And so this image is an example of a bare earth visualization. And this is actually Lowry Pueblo. If you can see, let me turn on my laser pointer here. The laser pointer, I have the dot kind of hovering right above the protective shelter that's built over part of the architecture at Lowry. That corresponds to the same area over on the hillshade on the left. And on the satellite image, you can't see a whole lot in terms of the landscape. But when you start to visualize these LiDAR point clouds through these various parameters, such as a hillshade, you do start to see features kind of popping out. So you can see additional architecture, for example, up here, a little bit to the north of Lowry. You can also see what we are calling a loop road, very, very clearly on the landscape. There are also, and these are kind of hard to see on this image, but I will show some more images later on. These features here, which are kind of a series of parallel ridges. And we've been referring to these as berm and swale features. And I'll talk more about these shortly, but the general thought at present is that these may be agricultural features. And these are features that are virtually impossible to see without the bare earth kind of visualization techniques. Okay, so this slide has a lot going on. Down at the bottom, I have a flow chart that is going to show up again on the next handful of slides. And it really illustrates the entire process of, again, going from our LiDAR acquisition through to our final derivative rasters, which are what we tend to use when we're doing all of this different visualization. And so if you'll forgive my kind of cartoonish drawing here, this is a depiction of the LiDAR process. Generally speaking, the way that this works is you have a light source and you are using that light and sending that light towards whatever you're trying to detect, whether it's a wall or in this case, the ground, the earth itself. And you can measure the amount of time it takes for that light to return to your detector, as well as the intensity of that light. And those values together tell you about how high up whatever object it's reflecting off of is, as well as what that object is. And so as you're traversing the landscape, you're sending light down, and you can use fixed wing aircraft, as I've drawn here. You can also use drones. There are increasingly more options available for LiDAR acquisition. But as you're traversing the landscape and you are sending this light down and you're measuring returns, you are generating a point cloud, which I have illustrated here. And that point cloud is each point in that point cloud has XYZ coordinates. So it's an actual physical space. But when we're working with LiDAR data, we're not actually usually working with these point clouds. Instead, we're working with digital elevation models, or DEMs, as I have depicted down here in the center of the bottom row. And these digital elevation models are actually raster images. And I point that out, and I'll talk more about this shortly as well, because there are a series of decisions that actually have to be made before you even get to visualization that can impact what you're seeing in that final visualization. And so also over here on the right side of the screen, I have some examples of different visualizations that you might use. Up on top, there is a 3D hillshade. And I have 3D in here because I was trying to be fancy and use ArcPro's 3D scene to show the point clouds a little bit clearer. But you can also do this with the 2D kind of top-down view as well. And this hillshade view allows you to basically position the sun anywhere you want to, including places where the sun would never normally be. And you can play with shadows that way and really emphasize certain features on the landscape, and it helps with visually identifying these features. And below that, I have an example of a kind of a composite visualization, and this is actually from the Relief Visualization Toolbox. It's a composite workflow that results in a visualization for archaeological topography, specifically designed for relatively flat topographic positions. And as you can see, I know it's a little bit small maybe, but there are features that pop out really clearly. And I should mention too, all of these are views of Lowry Pueblo as well. So it's kind of illustrating going through this entire process in one location. So part of the decision-making and going from your point clouds to your ultimate visualizations involves selecting which classes of points you're going to retain from the point cloud. When you're actually detecting those light returns, you're detecting everything. You're detecting vegetation, you're detecting the earth itself, you're detecting structures that are on the surface of the earth. And if you choose to keep or discard certain of those points, your ultimate visualization will reflect that. So on the left side, I have what we refer to as a bare earth digital elevation model. And this is the same view I showed on the previous slide. And on the right, I have a digital surface model. And this view retains all of the surface vegetation and structures and the like. And the reason it's important to think about which of these DEMs you might want to use has to do with the question that you're trying to answer. For example, if you are wanting to compare, say, the ground as it looked in 2018, when these LiDAR point clouds were acquired, with the ground as it looked back in 1950, and you have historic satellite imagery from 1950, you won't be able to subtract your vegetation from that historic digital elevation model that you can derive. But you will be able to create a digital surface model. And so if you have comparable digital surface models, you might be able to look at differences in growth of sagebrush, for example, to help you understand where maybe a field had been plowed in the intervening 75 years or so. So it's important to think about which of these elevation models is most applicable for your case. Oftentimes when people do line of sight analyses, they do want to use a digital surface model. Depending on whether your terrain is comparable with the paleo terrain that you're trying to model, because you want to know what the actual line of sight would have been, as opposed to the bare earth line of sight. So going back to point clouds, I have a little video here. I'll see if it plays. When you're collecting these point clouds, I wanted to emphasize that even though it looks really dense, as you zoom in close, there are gaps between the points that you're collecting. And this is important because when you're going from the point clouds to these actual visualizations, you have to figure out how you're going to deal with those gaps. So this blue square that I have over here on the left depicts a single square meter of ground area. And I have 3 dots that I threw in there just kind of at random that represent hypothetical point cloud locations. Generally, for the LiDAR data that we've been working with here at Crow Canyon, we have a LiDAR point density of about 2 points per square meter on average. If you look at LiDAR data that's been acquired specifically for archaeological purposes down in the Mesoamerican area, they're looking more for densities of 6 or more points per square meter. There's a lot denser vegetation. So to see through that tree canopy effectively, you do kind of want a higher point density. But that also impacts your processing requirements and the demands on your technology. So this is another example of selecting different classes of points. In this hypothetical square that I have over here, let's say that the black dots are ground points and the white point actually came off of a sagebrush. When you are selecting for just your ground points, you're only going to be working with those 2 ground points as opposed to all of the points. And that changes what you're going to be seeing on the landscape. And all of that is kind of bringing me to this slide and this discussion, which is that, again, we're not really working with the point clouds, we're working with rasters. And rasters are actually composed of numerous pixels, and each pixel has a single elevation value. So when we have, if you look in the lower left-hand corner here, our hypothetical square meter area with our points in it, we have to somehow go from those 3 elevation values or 2 elevation values, if you're looking at just the bare earth, to a single value for that entire square. And you can make decisions depending on your point density about how big that square is. In some places, you're able to get it down to a 0.5 meter by 0.5 meter square. In other places, people are using 90 meter by 90 meter squares. I happen to know that for our images, up here I have the hillshade view, and down here this is the digital elevation model, the bare earth view. I happen to know that each of these squares over here are a single square meter in size. But as you can see, this is a close-up of Lowry Pueblo again. And here you can see the actual architectural block of the Pueblo itself with the protective shelter over a portion of the architecture. And over here is the Great Kiva. So when you zoom in, this is on the entrance to the protective shelter. The pixels become very clear. And then down here on the DEM, I've done the same thing, but on the Great Kiva, just to illustrate that each of these pixels has a single value. So you have to decide how you're going to get that single value. And there are numerous ways of making that decision. A lot of it has to do with these mathematical interpolations. And I am just beginning to get into this myself. So instead of going into the details, I'm going to refer people to this article here, which is really well written and goes over a lot of the details about why you might want to consider certain interpolation methods, and they actually compare different interpolations for going from your point cloud to your raster. But this is an illustration of kind of the way that we at Crow Canyon have gone about processing our data, which is through the use of a free open source software called LAS-Tools, which uses, it takes your point cloud with your 3 points, and it turns it into a triangulated irregular network. So each point in your point cloud is made into the vertex of a triangle. And then it uses linear interpolation to assign a single elevation value to the entire square meter area or pixel, as you can choose your pixel size and your resolution for that entire pixel. So the reason I'm emphasizing this is for one, depending on the size of the features that you're interested in, you have to make sure that the resolution of your raster is small enough that you can see the features you're interested in. Oftentimes, archaeologists working with kind of quantitative or semi-quantitative approaches will be working with DEMs that are at 10 meter pixel sizes or 90-meter pixel sizes. And unfortunately, for a lot of the work we're doing right now at Crow Canyon, that will miss many of the features that we're interested in. But it's also important because depending on how you interpolate, you might emphasize elevation differences or you might average them. You might choose your elevations based on proximity, or you might choose the highest elevation, and that can change what you're seeing on the landscape. So this is another just example of once you've selected that one elevation value, you're left with your DEM, and then you can visualize that DEM. But already by the time you've gotten to this point, you've made choices about which classes of points you are including, how you're interpolating, and what your resolution of your raster is. So now I'm going to kind of speed through a little bit of what we're doing here at Crow Canyon. So where do we get this LiDAR data from? Well, the USGS, or U.S. Geological Society, has been publishing LiDAR point cloud data sets for much of the contiguous United States, as well as Alaska. And these LiDAR point clouds, they make the point clouds available. They also make DEMs available. And you can use whichever is most suitable for your project. We've been using the LiDAR point clouds because then we can control all of these processing steps along the way and be very consistent, which is important when you're identifying features on the landscape. But I have here an inset map showing the Four Corners region, and all of these areas shaded in green are areas where these LiDAR point clouds are available. And so here I have another close-up of the Four Corners region, and where I have this grayscale hillshade view, this is the area that Grant Coffey and Dylan Schwint had already processed for our study area. Part of my job here at Crow Canyon is to expand this area using the published LiDAR point cloud data. But this is our starting point. This is where we are concentrating most of our efforts. And really, we're focusing on the Central Mesa Verde region, so kind of over here in Southwest Colorado. But as I'll demonstrate on the next couple of slides, we're starting to see features that are very, very prevalent over here in Southeast Utah that we're using as reference for identifying features in Southwest Colorado. So on this image, or this slide, I have two images. One is of Goodman Point Pueblo, and the other is of Brewer Canyon and Brewer Mesa Top Pueblos. And these are both hillshade views. And what you can see in these images, and what's really difficult to see on the ground, are these loop road kind of features. You can kind of see them if you follow my laser pointer here. At Goodman Point, there was some documentation of one of these loop roads, but the second loop road was totally unsuspected until we looked at the hillshade view. I also wanted to draw attention to over here near Brewer Canyon and Brewer Mesa Top. There are, in this area to the upper right, some of these sort of ridges that you can see on the landscape. And these are also features that until we had access to this LiDAR data, we had only documented in a few places and or were completely unaware of. So this is an illustration. This is the exact same area. On the left, I have a satellite view. On the right, I have a hillshade view. And the satellite view, you can see that in this sector here, we have a lot of vegetation growth, specifically pinon juniper and sagebrush. And you can't see a whole lot. It's kind of just densely overgrown. But if you look at the hillshade view, you can start to see some of these ridge features that we are thinking might be agricultural in nature. And you can see kind of tracks where modern plowing and farm work and agricultural work has gone on, kind of in this cleared field area here. Those striations do show up in our hillshade view. So what I've been doing here at Crow Canyon is I actually put a grid over our study area, and I've been going just grid by grid with this hillshade view and looking for these features. And everywhere I see what I think might be these features, I'm drawing a little polygon and kind of earmarking it for us to come back to. And so far, this is kind of the extent of what I've identified. And this is just using the hillshade visualization. And I'm emphasizing that this is just with the hillshade visualization because, as I'll demonstrate on these next few slides, this is the slide we just saw a bit ago with the satellite view and the hillshade view. If I use the visualization for archaeological topography, this is the exact same area. This is the area that I identified with these ridges based on the hillshade view. If you look over here, you can see some features that are also present over in the plowed field area. And this is an area where people are still kind of actively working the land. So by applying these additional visualizations, we can actually see more of the landscape. And so I'm still going back through my grids with this additional visualization, and I don't have a revised set of polygons to share yet, but that's something I'm actively working on. This is a place called Hampton Pueblo, and it is, as you can see here, this is the sort of main architectural block for the Pueblo. We have right here a road segment or potential road segment. And then right here, we have an area of these features, again, these sort of ridge swell features. But if you look over on the VAT view, you can also see that down here, there are apparently a lot more potentially grid-like, potentially ridge and swale-like features that aren't really visible in the hillshade view. So it's very important to have multiple visualizations as you're doing this work. Now, this is a 3D view of that same area. This is one of the room blocks at Hampton. And this is that road segment that I pointed out, and that ridge swell feature that was visible on the hillshade. And this is to give an idea of how difficult these features are to see kind of on the ground. In this picture, I'm standing on top of one of these ridges. And if you look into the distance, you might be able to kind of see that there's another potential slight ridge there, maybe another one kind of right here. But it's not at all obvious. Even though these features kind of pop out on the visualizations, they're not easy to see on the ground. And they're almost invisible in many satellite images, which is why we've missed them for so long in so many places. So this is just a final example of why these multiple visualizations are important. This is actually near Crow Canyon Archaeological Center itself. This is a community center called the CIRC site. And over here on the left, you can tell that there's some architecture present. But when you apply the visualization techniques, you start to see individual pit structures and room blocks in construction. So it's very exciting to be able to look at the landscape with these different visualizations and identify features that you suspected were there based on the hillshade view, and then to see them kind of pop out is very cool. So Greg mentioned he had sent out a link to the Relief Visualization Toolbox. This is just some more information in case anybody wants that link again. You can download that link or download that toolbox from the GitHub repository for use in ArcPro. If you use QGIS, which is an open source software, you can actually install it directly as a plugin through QGIS and kind of skip going to GitHub. But these are some of the academic citations that are associated with that visualization toolbox. And the authors do a very excellent job, I think, of talking about their different visualization methods and techniques. So apologize, my dog is being a silly dog off in the corner.
And Katie, I just wanted to mention real quick, when I sent out the Journal Club announcement with the link to the Relief Visualization Toolbox, the link was directly to the university or the organization in Slovenia. It's project.
Okay.
So the link doesn't look the same as on your screen. So
okay,
I want to let everybody know that it's different.
Okay, that's a good starting place as well to read more about the toolbox. So these next slides, I'm going to kind of walk through the toolbox. I primarily use ArcPro, although I will have a little bit of a discussion about QGIS kind of towards the end. Um, on the left side of the screen, this is a snapshot or a screenshot of the visualization toolbox in ArcPro. And over here, I'm going to show the visualization that is generated. So for each of these visualizations, what you feed into the toolbox is the DEM. And in this case, I'm using all the bare earth DEMs. So this is a hillshade view. And as I mentioned earlier, I think the hillshade allows you to position the sun anywhere that you want to on the landscape. In this particular image, I have the sun positioned approximately northwest, or at about 315 degrees. And about 45 degrees above the horizon. But I could also put it due north or due south, and each of those positions will change the way that the shadows fall on the landscape. And as you can see in this image, you can't really see the ridge swell features out here near Lowry. And you lose a good part of the potential road segment here that's running up to the Great Kiva. You can see part of it, but from other visualizations, I know that that road segment is also generally visible down this way, but here we lose it. So it's very important when you're using these visualizations to consider the impact of your sun location on kind of the features that you're interested in examining. This is another visualization method called openness, and it's very similar to a technique that I'll show you just a few slides from now called sky view factor. But in this method, for each pixel, what the tool is doing is actually measuring how much of the sky is visible from that pixel. And so this is handy because unlike the hillshade, you're not necessarily introducing shadows from a single direction. So you're able to pick out features, in some cases, a little bit more clearly. This is a visualization of slope, and in this case, it's a slope percent. Slope is a very powerful visualization tool. It doesn't look like much on its own, but you'll see that when we combine all of these visualizations in just a few minutes, that it can really help us pick out features on the landscape. And then this is an example of the sky view factor visualization that I mentioned earlier, very similar to the openness visualization in terms of it operates as if each pixel is, you're standing there looking at the sky and how much of the sky you can see based on your relative topographic position with respect to all of your neighboring pixels tells the software what value to assign and how to draw it out. So all of that is combined. So when we talk about visualization for archaeological topography, generally what we're doing is we're actually pulling multiple visualizations into one single composite image. And that composite image is, in this particular case, really designed to highlight features that archaeologists might be looking for on the landscape. And so I have here a little graphic. This is actually from the visualization tool itself in ArcPro. That shows you the process that each raster is taken through. And I've got a fancy color-coded version here as well. So yellow is that visualization for archaeological topography. It's kind of everything summed up into one final raster. And along the way, we combine each of these other visualizations, each of these derivative raster products. And so we start with our bare earth DEM, then we create a hillshade. We also create a slope visualization, and we combine those two. We've also created an openness visualization and combined that with our first combination. So it's kind of a process of building on itself. And this is very, very powerful. This is another visualization of the visualization. In this case, I've actually swapped out the images for each of the kind of corresponding steps. And so you can see how the combined image here at the end tells you more than any single image on its own. And what's really cool about this visualization is here I've been using the bare earth DEM, but you could combine a bare earth DEM and a digital surface model if you wanted to explore, say, a particular vegetation type and how that's changed on the landscape over time. If you have a color satellite image, you could split that into its red, green, blue bands and use each of those bands individually as steps in this process and blend and combine. And other fields tend to do that more than archaeology. They'll use, I always forget the acronym for this, but it's a NDVI, basically a way of looking at how vegetation has changed over time and where vegetation is thriving and flourishing and where it's not. And in the context of trying to identify these features on the landscape, that can be important because it can help us understand where the landscape's been modified and where it hasn't been modified, and why maybe we're not seeing these features quite as widespread over here in Southwest Colorado as they're seeing over in Southeast Utah. And I should add too, I meant to add this a lot earlier. I'm a bit of a latecomer to a lot of this work. Winston Hurst and Fred Niles have been very diligently poring over the landscape in Southeast Utah and over here in Southwest Colorado and identifying many of these ridge and swale features or berm and swale features. They've looked at satellite imagery, and they've also spent a lot of time looking at the LiDAR and different visualizations. And there are two graduate students, Daniel Hampson and Logan Dean, who have been doing a lot of work looking at the LiDAR and identifying road segments and potential road segments kind of throughout the Four Corners region. And so they are all in the working group that we have at Crow Canyon, and we're all in discussion about what we think about different features and how we're going to define different features. And so it's a very exciting project to be a part of. And with that, I'm going to jump back into talking a little bit about GIS, or QGIS rather. I'm very new to QGIS, so I haven't investigated as many of these functions, but as I mentioned, the Relief Visualization Toolbox is available as a plugin just directly in QGIS. You don't have to figure out how to install any packages you download online or anything like that. It also has some advanced functionality in QGIS as compared to ArcPro, which is kind of exciting given that ArcPro is the proprietary version of the software. In QGIS, you can actually combine multiple visualizations all at one time. In ArcPro, if you're not using the built-in VAT functions, let's say you wanted to add another visualization like a slope and local relief model or simple local relief or a topographic position index, you would have to do that manually and blend and just keep track of which raster is which. But in QGIS, you can actually put in different rasters directly here and select different blending modes. And it's very, very powerful. Again, because you can work with a lot more than just DEMs. You can combine your DEMs with satellite imagery, for example. So I think I'm running close on time, but I should have enough, hopefully, to show this video. It may be a little bit redundant with what I've shown, but this was a screen recording of me going through some of the VAT use in ArcPro. So I start off by just showing the point clouds, which I already downloaded specifically for Lowry for this presentation, just to show that the point clouds are there. I filtered them so it's just the ground point clouds. And then I've gone through and I've created a DEM, and this DEM was done by a linear interpolation. You can't see much on the DEM, so I decided that just for demonstration purposes, I would turn on the hillshade layer. It's a little bit more exciting visually. So in ArcPro, we can actually use something called raster functions. So I don't know if a lot of people have worked with these imagery data sets very often, but our hillshade just for Southwest Colorado is more than 100 gigabytes in size. And so when you start to generate multiple rasters and you want to combine them for these multi-component visualizations, the file sizes can get quite large. But ArcPro uses a raster function, which means it kind of on the fly creates these visualizations as you're panning around the landscape, which is very cool. So in this case, because this is a built-in feature of the toolbox for this VAT flat, I've just gone in and I've selected my DEM, my kind of base raster. And there's an option here to calculate the 8-bit image. And that's helpful if you did want to do additional visualization and blend this image with something else down the line. You can actually create a standalone TIFF file. But if you don't check that box, you are not creating hundreds of gigabytes more storage. And so sometimes this process can take a bit to run. I think I let this run in real time here, and this is for a pretty large area. This is for our entire Hillshade DEM area for all of Southwest Colorado. So not just Lowry, but it's pretty quick, and you can see it's already added over here on the left, that VAT layer. It's just taking it a minute to figure out how to visualize it. And the reason I put this demonstration in here is because the VAT tool set can be very simple. It can be as quick as like install the toolbox, use the VAT combination option, drop your DEM, and then you're good to go. But you also have flexibility if you need to customize parameters. In some cases, you might have to make a choice about the nearest neighbor or the number of pixels you want to include in a resampling kind of process. And this is an example of, I've gone into the raster functions editor. And so this is just showing the workflow. This is all Kolkaj et al. They have developed this toolbox so that archaeologists can kind of use it as is, but again, with that flexibility, so you can really customize it and make it work for whatever your topographic situation is. Because in some cases, you may be interested in a topographic difference or an elevation difference of only a few centimeters. And in other cases, you might be working on the edge of a cliff and you might have hundreds of meters of elevation difference. So it's very powerful. And with that, I think I am wrapping it up. Thank you.
Hey, thanks, Katie. I just wanted to thank you for that presentation and open the forum to questions or comments. And one thing I wanted to talk about is the Berman swales that you're talking about as a form of permaculture agriculture. And you know, the Winston's, they've been finding them all over, especially in southeast Utah. He said not so much over here. But have you given any thought to the other possibilities? Because I know we heard in at the Pecos conference last summer the possibility that these might be an artifact of early agricultural practices around here, like the modern ones, chaining, taking two bulldozers, putting a chain between them, and clearing the landscape in about that width. So,
yeah, it's definitely something we have to be cautious about, and something we're talking about in the working group.
right.
I'm very lucky that I have Grant to consult with. He knows a lot more about agriculture than I do. And oftentimes I can kind of say, you know, Grant, does this look like it could be chaining to you, or do you think this could be maybe our features? And he's got a pretty good lock on, based on kind of the surrounding landscape modification that we see, on whether something might be these features that we're interested in potentially, or something else. It is definitely something that I'm going to work on, and specifically through the lens of using kind of historic satellite imagery and looking at where the landscape has been modified and where it hasn't been modified. Ideally, I'd like to find some 1930s Soil Conservation Service type imagery so that I can look at kind of pre-homesteading and post-homesteading for certain parcels of land, and kind of evaluate and maybe even come up with a glossary for what chaining might look like in terms of elevation profiles versus these features.
Right.
It's definitely an ongoing question, though, and ground truthing is a pretty critical component of all of this. And that's something, if anyone is going to the SCAAS, one of my coworkers is presenting a paper for us about some ground truthing work we did at Hampton, actually. So it's still very much something we're thinking about and talking about. Kind of a non-answer, I guess.
That's okay. And the other thing I was curious about is the imaging that you've been putting together for Southeast Utah and Southwest Colorado through Cook Canyon and your working group. Is there a possibility that would be open to researchers at some time in the future, or?
Oh, um, that is something that we have not talked about in a lot of detail. What I can say is the LiDAR point clouds themselves are publicly available. The DEMs, they have what they call original project resolution DEMs available on that same 3D elevation project USGS website. Those tend to be available at 1 meter resolution as well. Um, it's you would then have to process them through all of this subsequent visualization. Um, I don't know whether I can't speak for Winston or Fred or Daniel or Logan or anyone else. As far as making the images themselves available, they are very big images, so I actually don't know how that would work as far as file sharing goes. They're too
Sure.
big to email. You would need a very large like Dropbox or OneDrive.
Right.
So
Yeah.
I don't know. We'll have to give that more thought.
Yeah, we're running into that in terms of sharing photogrammetric models too. How do we share these very large files? So,
Yeah, it's a challenge for sure.
does anybody else have any questions or comments? Nobody? All right. Well, in that case,
Is it
we'll.
was
Pardon?
it too much on the point clouds?
I don't know. Just a wonderful presentation. We want to thank you very, very much. And I'm going to go ahead and stop the recording. Let's see how we do that. I can't.